Hi, everyone, and welcome to week 3 of Introduction to Logic. This week, we are going to talk about truth tables for propositions and truth tables for arguments. If you need a refresher on anything we've covered in the course so far, including the definitions of the propositional logic operators, be sure to go back and watch the videos for week 1 and week 2 to get caught up and up to speed if you need to. Let's go ahead and dive in. Before we get started, I want to do just a quick refresher on the definitions of these propositional logic operators that you should have down pat by now, but everything we're going to do this time and next week depend on your ability to intuitively recognize the definitions of these logic operators and apply them in truth tables. So let's go ahead and dive in. If you remember, a truth table is a way of listing out all of the possible combinations of truth values that make up a compound statement so you can see the resulting truth value of the overall statement. So let's start really simple. If you remember, the easiest logic symbol that we looked at was a negation. So if you have any statement P, whether simple or complex, that has two possible truth values. P is either true or P is false. And the negation, this tilde symbol right here, just negates that statement. So it has the opposite truth value of the statement it negates. So if P is true, not P would be false. And if P is false, not P would be true. And these are the values for that negation. But you can see that the values for that symbol are dependent on the values of P, and that's what the textbook means by truth functionality. The truth value of a compound statement is dependent on the truth values of the simple statements that make up that compound expression. Okay, that's one of the symbols. Let's move on. So we also last week looked at the dot operator, which is a conjunction. So if you have a statement like P and Q or P dot Q, in this case, there are four possible combinations of truth values. P is either true and Q is true, in other words, both of them are true, or P is true and Q is false, or P is false and Q is true, or P and Q are both false. And if you remember from last time, the definition of the conjunction is that a conjunction is true only if both of the two conjuncts are true. That's what the word and means in English. So in the first row, P and Q are both true, so the conjunction will be true, and we write a T underneath the dot for that. In the next row, it's not the case that P and Q are both true, so you end up with a false conjunction, and so we're going to put an F underneath that dot. In the third row, same thing. It's not the case that both of the two conjuncts, P and Q, are true, so we're going to put an F there for false in that third row. And same thing in the last row. In the last row, it's not the case that P and Q are both true, so the conjunction will be false. So you can see in this case, there's only one row where the conjunction is true, and that's when P and Q are both true. Again, no matter whether P and Q are simple or complex, in other words, no matter what P and Q stand for, that conjunction will only be true if P and Q are both true. And by convention, we usually circle the final column underneath the main operator of a statement. So we know which column we need to look at when we're comparing statements or evaluating a statement, and eventually when we're evaluating an argument. Okay. Let's look at the wedge operator. So if we have a statement like P or Q, and again, if you remember, the wedge operator is an either or statement in English. Again, there are four possible combinations of truth values. P and Q are either both true or, or P is true and Q is false, or P is false and Q is true, or P and Q are both false. And like we use either or in English, this statement is true if at least one of the two conjuncts is true. In other words, if either P or either Q is true, then we end up with a true disjunction. So in the first row, it is the case that at least one of the two disjuncts is true, so we end up with a true statement. In the second row, at least one of the two statements is true, so we end up with a true statement. Same thing in the third row. But in the last row, it's not the case that at least one of the two statements is true, so we end up with a false statement. As you can see, the truth table for a disjunction looks quite different than the truth table from a conjunction a moment ago. And again, by convention, we're going to circle that to indicate that's the main column for that statement. Okay, let's look at an let's look at a conditional statement. If we have a statement like P implies Q, remember this horseshoe symbol is an if-then statement. So this could be read as if P then Q, or sometimes P implies Q. Let's list our possible combinations of truth values. Either P and Q are both true, or P is true and Q is false, or P is false and Q is true, or P is false and Q is false. Now this one's a little tricky. You might just have to memorize this. If you're having trouble with this truth table for the horseshoe symbol, go back and watch the week 2 video where I cover the definitions of these operators in a bit more detail than I'm doing here for review. If you remember though, there's only one row in which this implication is false. That's when the antecedent is true and the consequent is false in that second row. In all of the other rows, you end up with a true statement. And again, that can be a little counterintuitive. You might just have to memorize that. If you're having trouble with that, go back and watch the week 2 video or review section 6.2 in your Hurley textbook where these operators are first defined in detail. So that is an implication or an if-then statement. And finally now, let's look at a biconditional statement, or what's sometimes called equivalence, or an if and only if statement. So if we have a statement like this, P triple bar Q, the name of the operator is triple bar, but sometimes it's referred to as a biconditional operator or an equivalence operator. Let's list our possible combinations of truth values. Either P and Q are both true, or P is true and Q is false, or P is false and Q is true, or P and Q are both false. So the name of this operator, equivalence, really helps here. What we're really looking for is whether these two components, P and Q, are equivalent or not, if they have equivalent truth values. If the answer to that question is yes, they have equivalent truth values, you'll end up with a true biconditional. And that happens in 2 rows, in the first row and in the last row. In the first row, P and Q are both true. They're equivalent, so the equivalence will be true. In the last row, even though P and Q are both false, they have equivalent truth values. They're both true. Sorry, excuse me, they're both false. So the equivalence is going to be true because they have equivalent truth values. But in the second and third row, they have opposite truth values. In the second row, P is true and Q is false, so the equivalence is false. They're not equivalent. Same thing in the third row, P is false, but Q is true. They're not equivalent, so the equivalence will be false. And that is the truth table for a biconditional. So make sure you have the definitions of these logical operators down in terms of their truth tables. That's how the operators are defined. And I think you'll see from doing the homework from week 2 last week and the homework for this week that your ability to do the homework is highly dependent on your ability to have these truth table definitions of these operators down pat. You really need to make this as intuitive as you can for yourself, getting lots and lots of practice on it. Okay, let's go ahead and dive in. What we're going to do now, we're going to talk about truth tables for statements. What we need is a general way to create a truth table for any degree of complexity in a single statement in propositional logic. So I'm going to start with a very simple example, and then we're going to look at another more complex example and look at some of the things you can do to evaluate the nature of a statement using truth tables. I'm going to use an example from your textbook. This is an example that's used on page 354 of your textbook. Suppose you have a statement like A or not B implies B. The first thing we need to do is we need a method for creating a truth table for this statement. The first question you need to ask is how many rows you're going to need. Even when we were looking at the definitions of the logic operators, you could see that like the negation symbol only needed 2 rows because there were only 2 possible combinations of truth values. For the other 2-place operators, you needed 4 rows to exhaust all the possible combinations of truth values. And I think you can see even from those examples that the number of rows in a truth table are exponential. They're a function of the number of simple statements you have. So in this statement here, we have 2 types of statements. We have A and B. And even though the letter B is repeated, there are only 2 types of statements, just A and B. And of course, if you remember, these are statements. These are either true or false. So this means there are only 4 possible combinations of truth values, right? Either A and B are both true, or they're both false, or one is true and the other one's false, or vice versa. The other one is true and the first one is false. But you can see from this, there's a general method. The number of rows in a truth table, I'm going to put this down at the bottom of the screen. Number of rows, oops, excuse me, write a little nicer than that. How about that? So the number of rows is going to be 2 to the n, where n is the number of simple statements that you have, which is basically 2 times 2. We have 2 simple statements here, A and B, so we have 2 times 2, or 2 to the 2nd power. If we had A, B, and C, it would be 2 times 2 times 2, which would be 8 rows. In other words, that would be 2 to the third power. The book goes into this in some detail. I think you'll be able to pick this up by example. So in this case, I think it's pretty clear that we're going to need 4 rows. 2 times 2, or 2 to the second power, is just 4 rows. So let me erase this bit at the bottom of the screen, and we'll dive in. So when you're starting to create a truth table, we'll get rid of these marks as well. There we go. When you're starting to create a truth table, the first thing you do is go underneath the first letter. In this case, the first letter is A. If we know we're going to have 4 rows, what you do is you take that number and cut it in half. If you're going to have 4 rows, you set half of those rows to true and half of those rows to false underneath that first letter. Then you move over to the next unique letter. If we had run into A again, we'd skip that and go to the next unique letter. So we go over to the next letter, which is B, and we cut that number in half. If under A we had 2 trues and 2 falses, under B we're going to have 1 true and 1 false. And then we're going to repeat that all the way down, 1 true and 1 false. And where that letter is repeated, we're basically going to copy that column underneath that same letter. So if we have true, false underneath B, underneath the next instance of B, we're going to have true, false, true, false. And we'll look at a more complex example with more simple statements in just a minute, but let's run through this simple example together. Now, if you remember when you were doing truth functions in week 2, one of the first things you needed to do was identify the main operator of the statement. And right here, this horseshoe is the main operator. That's the operator with the largest scope that governs the entire statement. But we can't figure out the value of that main operator until we figure out the values of the operators that have a smaller scope. So when you're doing a truth table for a statement, you start calculating away, figuring out the values that go underneath each propositional logic operator, but starting with the connectives that have the smallest scope, that are nested and buried as far down inside the parentheses as you can find, working your way out until you get to the operators with the largest scope. And when you figure out the values that go underneath that main operator, those are going to be the values that represent the possible truth values for that entire statement. So let's go ahead and dive in. I'm going to do each column in a different color here, just to make it easy to follow. The operator here with the smallest scope is actually this operator here. It's this negation right in front of B. And once you know the values of B, which we already have, the values of the negation will be easy to find, right? If B is true, not B is just false. And if B is false, not B is going to be true. Same thing here and same thing here. False, true, false, true. The operator with the next largest scope, I'm going to do it in a different color still, is right here. Now, just like when you were doing truth functions, you have to be really careful that you're using the correct columns to figure out the values under any given operator. The two things that are connected by this wedge are A and not B. So if we're going to figure out the value of that disjunction, that wedge, we need to look at the values under A, and we need to look at the values underneath that wedge, that tilde, because that tilde represents the value for not B. So in other words, we're going to be looking at this column and this column to figure out the value for the wedge. And if you remember, a wedge is an either or statement. So if at least one of those two disjuncts is true, we're going to end up with a true disjunction. So in the first row here, we've got a true and we've got a false. At least one of those two is true. So we're going to end up with a true disjunction in that row. Same thing in the next row. At least one of the two, either A or not B, is true. So we end up with a true disjunction. In the next row, however, we end up with a false disjunction because it's not the case that at least one of those two disjuncts is true, right? A is false and not B is false. So we end up with a false statement. But in the last row, at least one of the two is true, not B is true. So we end up with a true disjunction. I'm going to do just a little bit of cleanup here, erasing these extraneous marks. There we go. And those and those and those. So now we're in a position to figure out the value for the main operator. And I'm going to pick a prettier color here to use. Let's use lavender. So the challenge when doing truth tables is always figuring out which two columns you need to look at to figure out the value for any given operator. So if this horseshoe is the main operator, that horseshoe connects this entire parenthetical expression on the left with B on the right. But inside those parentheses on the left, that wedge is the main operator inside the parentheses. And of course, the horseshoe is just connecting B. So the two columns we need to look at are right here. In other words, we need to look at this column and we need to look at this column to figure out the value for that horseshoe operator. And again, just for review, there's only one case when a horseshoe operator is false. That's when the antecedent is true and the consequent is false. So what we do, we just go down row by row by row, checking each possible combination and listing the resulting truth values. So in the first row, we've got a true disjunction and the letter B is true. So we have true implying true, and that would be true. In the next row, we've got true implying false, and that's our one case when a conditional is false. In the next row, we've got false implying true, so that's going to be a true conditional. And in the last row, once again, we've got something true implying something false right here, and that's going to give us a false conditional. And these are the values that we care about that represent the possible truth values for this entire statement, because those are the values that are listed underneath the main operator. So that is a very simple example of how to create a truth table for a compound statement. Now let's look at a slightly more complicated example with more rows, and you can see how this works in a bit more detail. So again, I'm going to use an example from the textbook. This is an example from the textbook, page 356. Let me write it out here. Okay, we've got C and not D implies E. So in this case, we have three types of letters. We've got C, D, and E. And if you remember, the number of rows is going to be 2 to the n, where n is the number of types of simple statements you've got. So in this case, that'll be 2 to the third, or 2 times 2 times 2, or 8 rows. To start building the truth table, you go under the first letter, and if you know you're going to have 8 rows, you take half of those and set them to true. So we're going to have true, 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 false, 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 false. Then you move over to the next unique letter, which is D. And if we had another C here, we would skip that and go to the next unique letter. But here we just go right over to D. If we have 4 trues and 4 falses under C, under D, we're going to cut that number in half. 2 trues and 2 falses. 2 trues and 2 falses. Oh, I just made a mistake right there. Let's fix that right now. True, true, false, false. True, true, false, false. That's better. And then under the next unique letter, which is E, we're going to cut that number in half. So 1 true and 1 false. 1 true and 1 false. 1 true and 1 false, all the way down. And that will exhaust all the possible combinations of truth values. If C, D, and E are either true or false, there's no possible combination that's not listed on this truth table now. One thing I want to interject really quickly is that each row of this truth table represents a different possible way the world can be. You can call it a different possible world or a different possible scenario. Sometimes we'll call it a different case. Really what's going on here is that if C, D, and E are statements that are either true and false based on the way the world is, the statements could all be true, or 2 of the statements could be true and the other one false. And each row exhausts a different possible way the world could be. Again, keeping in mind that these letters stand for statements that really do refer to things in the world that are either true or false. Okay, let's go ahead and dive in. So the very first step, as in the previous example, is to start with the connectives that have the smallest scope and work outward until you get to the main operator. And the main operator is this horseshoe right here. So we're not going to do anything with that column until the very end. We're going to start with the connectives that have the smallest scope and work our way outward until we get there. In this case, the connective with the smallest scope is this tilde right here. So that's what we're going to do next. And this is very easy. The tilde just negates the statement D, and we have the values for D. So underneath the tilde, we're just going to write the opposite values of D. If D is true, the tilde will be false. And if D is true, the tilde will be false. In the third row, the D is false, so the tilde will be true. Same thing here. And I think you can see this, it's the same pattern, but in reverse. If D is true, true, false, false, all the way down, we're going to have false, false, true, true, false, false, true, true. Just the opposite values of D. Okay. Now, again, we're starting on the inside and working our way out. We're not even concerned with the main operator yet. The connective with the next largest scope is this dot. And that dot connects C and it connects not D. So the two columns we care about are the column underneath C, but the values for not D are not the values for D, but the values underneath that tilde. That's what represents the values for not D. So the two columns we care about for the purpose of that dot are those two columns right there that I've indicated with the green arrows. And the dot is a conjunction, so that corresponds to the English word and. So that conjunction will be true only if C and not D are both true. If either one is false, we end up with a false statement. And that's what we have in the first row. They're not both true, so we end up with a false statement. Here we have a true and a false. They're not both true, so we end up with a false statement. Here we have true and false, so we end up with a false statement. Here we have true, and that's a case where C and not D are both true, so we end up with a true statement. I think you can see that from that row right there. And in the rest of the rows, they're not both true because it's the values under C are false all the way down. So the rest of the way down, we're not going to end up with a true conjunction because it's not the case that both of the two conjuncts are true. And those are the values that represent the dot operator. Let me do just a little bit of cleanup here, make it easier for you guys to see. So now we are in a position to get the values underneath that horseshoe, the main operator of the statement. But this is where you have to be really careful not to make a mistake. So if that is the main operator, the column underneath the horseshoe, you need to make sure you're drawing from the correct two columns to get the values for that horseshoe. And in this case, that horseshoe is connecting this entire statement in parentheses with the letter E. So one of the values we're going to care about are those values under E. But inside those parentheses on the left, this dot is the main operator. So that's the value that's being connected with E by means of that horseshoe. So those are the two columns we're going to look at to determine the values of the horseshoe, which is the main operator of the statement. Now I'm going to be really heavy-handed here and circle things as I go so you can follow exactly what I'm doing. In the first row, this dot is false, but E is true, and that's going to be a true conditional, according to the definition of a conditional. In the next row, we've got false implying false. That's going to give us a true conditional. If we have false implying true, that's going to give us a true conditional. But in this next row, we have a true conjunction. E is false. That's going to give us a false conditional according to the definition of that horseshoe operator. If we have false implying true, that's going to give us a true conditional. False implying false, that's going to give us a true conditional. False implying true, that's going to give us a true conditional, and false implying false is going to give us a true conditional. Okay, so again, once you have the values underneath the main operator, those are the values that represent the overall statement. I'm going to circle those in blue here. Those are the values that represent the possible values of that entire statement. And again, each row represents a different possible way the world can be. So if C and D and E are all true right there, you end up with a true conditional. If C is true and D is false, but E is true, you end up with a true conditional there. So that's how you figure out the truth value of an overall statement based on the truth values of the components. What you were doing last week is essentially doing one row of the truth table at a time. Each one of these rows represents a different truth functional calculation. Basically, you're exhausting all the possible combinations of truth values, but it's essentially the same activity as you did last week, except you generally complete them one column at a time, using the same pattern though, starting with the connectives that have the smallest scope and working your way outward until you get to the connective with the largest scope. Okay, let's move on. Happily, there are some things you can learn about individual statements that are pretty handy, and I think you'll see why here in just a minute. One thing you can do is you can classify statements. And all statements can be classified into one of three different kinds. One is a tautology. A tautology is a necessary truth, sometimes called a logical truth. A statement could also be a self-contradiction. You can almost figure out what self-contradiction means. Self-contradiction is going to be necessarily false. So a necessary falsehood, or sometimes called a logical contradiction. Okay, and if it's neither of those, that's called a contingent statement. And a contingent statement is, it could be true. Oops. Could be true, and it could be false. So let's look at how to use a truth table to decide what kind of statement you're looking at. And actually, before we do that, I want to dwell on these just a little bit. So I kind of make a conceptual connection to the truth tables we're about to look at. If a tautology is necessarily true, that means it's impossible for it to be false. It means no matter what statements make up that statement, the tautology will always end up being true. In other words, underneath the main operator of a tautology, you'll end up with true all the way down. That means no matter how the world is, no matter what the truth values are of the simple statements that make up that compound statement, you'll end up with a statement that's always true. For a self-contradiction, it's the exact opposite. That's a case where underneath the main operator of a statement in a truth table, you'll end up with truth values that are false all the way down. And that means it's impossible for the statement to be true. It means the statement is going to be false no matter what the truth values are, no matter how the world is. And a contingent statement could be true or could be false. In other words, underneath the main operator, you'll end up with values that are sometimes true and sometimes false, at least one true and at least one false. That means that statement, the truth value of that statement really is dependent on how the world is and what the truth values of those simple statements are. So let's look at a few examples of these. Let me move to the next page. Here we go. Okay. Let me write out a couple of examples here. So these are examples from page 359 of your textbook. First example is like so. In fact, I'll do these examples side by side so you can see the difference. Okay, so here we've got two different statements. We're going to create truth tables for each of these statements, and we're going to see what we end up with underneath the main columns of each. So in each of these statements, we only have two types of letters, G and H. So we're only going to need 4 rows, 2 to the second power. Underneath the first letter, in this case G, we're going to set half of those to true and half of those to false. So true, true, false, false. And wherever you see a G, we're going to repeat that. True, true, false, false. Same thing here. True, true, false, false. Same thing here. True, true, false, false. Under the next letter over, H, we're going to cut that number in half and alternate. True, false, true, false. Same thing here. True, false, true, false. Under the next instance of H, true, false, true, false. Same thing here, true, false, true, false. And I think you can see you need to be really careful that you enter these initial truth values correctly. If you end up with a stray T or F in the wrong place, that will throw off all of the resulting truth values we get, and you'll have made a pretty massive mistake. So go really slowly and cautiously and make sure you're entering these initial values in your truth table correctly. Okay, I'm going to blaze through this. We're going to start with the connectives that have the smallest scope and work our way outward. So let's start here on the left. The connective with the smallest scope is this horseshoe that's buried inside these parentheses, and our main operator is right here under that horseshoe that connects that bracketed expression on the left with H on the right. But we're not going to start there. We're going to start with the connective that has the smallest scope, which is this horseshoe buried inside the parentheses on the left. Okay. So the first thing we're going to do is apply the definition of that horseshoe operator to these truth values. And here we've got G and H. G implies H. That means true implies true. That's going to give us a true conditional. In the next row, however, we've got true implying false, and that's going to give us a false conditional. In the next two rows, we've got false implying true. That'll give us a true conditional, and false implying false. That's going to give us a true conditional. And again, I can't emphasize this enough. If you're having trouble with the definitions of these logical operators, go back to week 2 and watch the video for week 2 and look at the examples that are given in the textbook for the definitions of these logical operators. Everything we're going to do this week, next week, and frankly for the next many weeks is going to depend on your having that down pat. So make sure you get lots of practice on that. Okay, to figure out the value of this dot operator, which is the connective with the next largest scope. Again, we're starting on the inside of the parentheses and kind of working our way out until we get to the main operator. That dot connects this parenthetical expression, G implies H, and the value that we care about there is this value under the horseshoe that we just calculated, and the value for G. So we've got something true implying, and something true. It's a dot, true and true. That's going to give us a true conditional. Conjunction, excuse me. In the next row, we've got something false and something true. That's going to be false. In the next row, we've got something true and something false. That's going to give us false. And in the last row, we've got something true and something false, and that's going to give us false. So I'm going to erase these little arrows. Now we're in a position to figure out the value for the main operator. I'm going to do that in a different color because that's the column we're most interested in. So this main operator, this horseshoe, connects this entire bracket expression with H. I think that's pretty easy to see. But the main operator inside the brackets is this column we just figured out underneath the dot. And of course, the conditional connects H as well. So those are the two columns we care about. And again, I'm going to circle these so you can see what I'm doing. It's going to be a little messy, and the end result will be a little messy, but it'll be easier to follow if I circle this as I'm going. So here, we've got a true conjunction, and H is true. That's going to give us a true conditional. In the next row, we've got a false conjunction. Again, that's the main operator inside the brackets. So something false implying something false, that's going to give us a true conditional. Something false implying something true, that's going to give us a true conditional, and something false implying something false, and that is going to give us a true conditional. Doing just a little bit of cleanup here so it's easy to look at. What I'm going to do is circle this column because that column represents the possible values for that statement. And you can see here that it's impossible for the statement to be false. This statement is necessarily true. In other words, no matter which row represents the different ways the world could be, no matter which row represents the actual world, you end up with a statement that's going to be true. It's true in all possible situations. So this is a tautology. Okay, it means it's a necessarily true statement or a logically true statement. It's impossible for it to be false. In other words, no matter what G and H stand for, no matter whether G and H are true or false, this complex expression, if G implies H and G, then H, all of that taken as a whole is going to be a true statement no matter what. That's what a tautology is. Let's do the example on the right for comparison. So again, we're going to start with the connectors that have the smallest scope and work our way outwards until we get to the main connective. And here the connectives with the smallest scope are these tildes. These should be pretty easy to figure out. They're just the opposite of the things they're negating. So let's start at the very right. If H is true, false, the negation will be false, true, true. Same thing in front of the G. We've got a tilde in front of the G. That's a negation of G. So if G is true, true, false, false, starting at the top and going down, that negation will be false, false, true, true. Next, we need to figure out the values for this dot operator. Now, here's where you have to be really careful. We spent a lot of time on this in week 2, but I want to reiterate it here, that this dot is connecting not G and it's connecting not H. So it's not connecting G and H, it's connecting the negation of G and the negation of H. So the two columns that we care about for figuring out the value of that dot are those two columns that I've indicated with the arrows. And the dot is a conjunction. So if both of the two values are true, you'll end up with a true conjunction. If they're not both true, you'll end up with a false conjunction. So here we've got false and false. That'll give us a false conjunction. False and true, that'll give us a false conjunction. True and false, that's a false conjunction. But in the last row, not G is true and not H is true, so that'll give us a true conjunction. And I'm going to erase my little placeholder arrows here. Okay. Let's continue. On the left side of that statement, we have G or H inside parentheses, and that wedge is a disjunction. That means that that disjunction will be true if at least one of the two disjuncts, G or H, is true. In the first row, it is the case that at least one of them is true, so we end up with a true disjunction. Same thing in the next row, at least one of the two is true, so we end up with a true disjunction. Same thing in the next row, but in the last row, it's not the case that at least one of them is true, so we end up with a false disjunction. And now we're in a position to figure out the value of the main operator, which is right here, that triple bar. As a quick reminder, the triple bar is also a biconditional or an equivalence. That means we're looking for two values that are equivalent. If the two values we're interested in are equivalent, you'll end up with a true biconditional. If they're not equivalent, if they have opposite truth values, you'll end up with a false biconditional. So the two columns that we care about are this column right here. That's going to be the main operator inside those parentheses. I think that's pretty easy to see. And over here in these parentheses on the right, it's the value underneath the dot that we care about because that's the main operator inside that set of parentheses. So I'm going to circle these as I go, as before, just to make it easy to follow. So here we've got a false statement on the left and a false statement on the right. Those are not equivalent, so that biconditional will be false. In the next row, we've got true and false. Those are not equivalent, so we end up with a false statement. In the next row, we've got a true statement over there on the left and a false statement over here on the right. Those are not equivalent, so we end up with a false biconditional. And in the last row, we have false on the left, true on the right, so we end up with a false biconditional, again, because they have opposite truth values. And when we're done, we're going to circle the column underneath that main operator. Now, in this case, unlike the first statement, the statement is always false. It's impossible for the statement to be true, and this is a self-contradiction, sometimes called a logical contradiction. Over here, tautology is sometimes also called a logical truth. Okay. And I think you can see there's another possibility here. Some statements aren't always true or always false. Some statements end up with a column where you have some T's and some F's. Those would be examples of contingent statements. We might as well do one of those. The book doesn't really show one, but I can find one here for us to do. Let me grab one from the book here. So if you look at this statement here, not L implies not K. If we make a truth table for this really quickly, and I'm not going to spend much time on this so we can get moving, but there are 4 possible rows. Under the first letter, 2 trues and 2 falses. Under the next letter, true, false, true, false. The connectives with the smallest scope are these negations. So the negations just have the opposite value of the statement they apply to. So I'm going to fill out the values for those negations really quickly, like so. And to get the values for the final operator, again, just to be really clear here, the main operator is this horseshoe. That horseshoe connects not L and not K, which means the two columns we care about are those two columns for the purpose of figuring out the values underneath that horseshoe. So here we have something false implying something false. That'll give us a true conditional. Something false implying something true. That'll give us a true conditional. But here's our exception, something true implying something false. That'll give us a false conditional. And true implying true. That'll give us a true conditional. And once I figured out the values underneath the main operator, I'm going to circle those. And here you can see that the statement is sometimes true and sometimes false. In other words, if L is true but K is also true, you end up with a true conditional. If L is true and K is false, you end up with a true conditional. But in the third row, suppose the world were such that L is false but K is true, that would give us a false conditional and true in the last row. So this is a contingent statement. That means it's sometimes true and sometimes false, basically based on how the world is. Is the world such that the simple statements that make up the statement are true or false? And you get a different outcome in each of the possible combinations here. So a contingent statement is one in which you end up with some T's and some F's, at least one true and at least one false underneath the main column of a compound statement. So this is one handy thing you can do with truth tables, is figure out what kind of statement you have. Do you have a statement that's necessarily true, or a tautology, necessarily false, or a self-contradiction, or a contingent statement that could be true or could be false? And what is it contingent on? Basically how the world is. Each one of these rows represents a different possible state of the world, or a different possible way the world could be. Okay, so that's one thing you can do with truth tables. Let's look at another thing you can do. Let's look at what the textbook calls comparing statements. So if you look at pairs of statements, there are a few things that you can learn from pairs of statements. Statements could be logically equivalent. They could be contradictory. They could be consistent, and they could be inconsistent. So let's talk about the definitions of each of these terms. I think logically equivalent is pretty easy to figure out. Two statements that are logically equivalent have identical truth values in all possible rows. Statements that are contradictory have opposite truth values. Again, in every row of the truth table underneath their main operators. If two statements are consistent, that means it's possible for both statements to be true. Oops, true. In fact, let me write that a little more clearly. There we go. And if two statements are inconsistent, that means it's impossible for both statements to be true. And you can learn all of these by looking at truth tables for two different statements and comparing the end results. So I'm going to run through a series of examples that your textbook uses, and then we're going to look at some examples from the exercises before we move on to evaluating arguments using truth tables. Okay, so I'm going to look at a couple of examples given by your textbook. Let's look at these two statements here. K implies L, and over here on the right, we're going to have not L implies not K. We're only going to need 4 rows because there are two simple letters, K and L. So underneath the first letter, we're going to have 2 trues and 2 falses. And we're going to repeat that over here. True, true, false, false. Every time you see another instance of the same letter, copy the same values. Under the next unique letter, which is L, we're going to have 1 true and 1 false. 1 true and 1 false, repeating all the way down. And we're going to copy that every time we see an instance of L. Oop, just made a mistake. Let me fix that. There we go. True, false, true, false. Okay, on the left, we just have a single operator. It's just a horseshoe. That's going to be false only when you have a true antecedent and a false consequent, which we have right there. And it's going to be true in all the other rows. And again, that just follows from the definition of the conditional operator. On the statement on the right, we need to start with the negations because this horseshoe doesn't just connect L and K, it connects the negation of L with the negation of K. So we have to start with the values for the negations before we can figure out the values for that horseshoe. So we have the values for L, that's true, false, and the negation will have the opposite value, false, true, true. For the negation in front of the K, if K is true, true, false, we're gonna have false, false, true, true. And finally now, we can figure out the value underneath that horseshoe. Again, you have to be a little careful here because that horseshoe connects not L with not K. So the two values we care about are right here and right here, the values underneath those negations. So make sure you're using the correct columns to figure out the value for any given operator. Here we have something false, implying something false. That'll give us a true conditional. The next row, we've got something true, implying something false. That'll give us a false conditional. The next row, something false, implying something true. That'll give us a true conditional. Something true, implying something true. That'll give us a true conditional. I'm going to use a different color here to highlight the main columns. But once we have the values underneath the main columns, you want to circle those. And then we're going to compare these two final columns for these two different statements. And you can see here that these two columns are identical. When one is true, the other one is true. When one is false, the other one is false. So because they're identical all the way down, these two statements are logically equivalent. It means they make the same exact truth claims. They're just two different ways of phrasing the same exact claim. Okay, so that's logical equivalence. Let's look at an example of two statements that are contradictory now. So here's two other statements. K implies L. And over here on the right, our second statement is K and not L. Let's show that these are contradictory. So we're going to make a truth table under the first letter, two trues and two falses. Again, that's only because we have two letters, K and L. If we had a third letter, we would need 8 rows. If we had 4 letters, we would need 16 rows, and so on and so forth. So you can see truth tables get pretty unwieldy and pretty massive very quickly. So they're a useful way to deal with these short statements, but when you get into much longer statements and longer arguments, more complex arguments, you're going to need a different method than truth tables because you could fill up the whole wall with a truth table very quickly. Okay, so under K, 2 trues and 2 falses. Under the same K over here, 2 trues and 2 falses. Under L, 1 true and 1 false. 1 true and 1 false. Same thing over here, 1 true, 1 false. 1 true and 1 false. Okay. On the left side, K implies L. That's just a horseshoe operator. So same thing as before. You only have one case when that conditional is false. That's when the antecedent is true and the consequent is false. In all the other cases, you end up with a true statement. And I'm going to circle that as the main operator, the values underneath the main operator. Okay. Over here on the right, the main operator is this dot, but that dot is connecting K and it's connecting not L. We don't have the values for not L yet. We just have the values for L. So the values of this negation are opposite of those of L. So if L is true, the negation will be false. If L is false, the negation will be true. Like so. And now, again, just be really careful here because you want to make sure you're looking at the right columns. This dot is connecting K and it's connecting not L. So the two values we care about are the values under K and the values under that negation, not L. So we've got something true and something false, and that's going to be false. Remember, a conjunction or the dot operator is true only if both of the two conjuncts are true. That's what we have in the second row. We've got true and true, so we end up with a true dot. And in the next 2 rows, we're going to end up with false. I think that's pretty easy to see. And I'm going to circle those values. Now, comparing these two columns, you can see that they're opposite of each other. When one is true, the other one's false. When one is false, the other one's true. all the way down. In all possible combinations, you have opposite truth values. So these two statements are contradictory. In other words, they're basically negations of each other. The statement on the right is the negation of the statement on the left and vice versa. That's why they have opposite truth values. They contradict each other. They can't both be true at the same time. Okay, let's move on. Let's talk about consistency and inconsistency now. Like I said a moment ago, two statements are consistent if it's possible for them to be true together. Whether or not they're actually both true, it doesn't matter. It's whether it's possible for them to be true. So let's look at two statements that are consistent with each other. First statement is K or L. The next statement is K and L. Okay, let's make a truth table for these. Same thing, we're only going to need 4 rows. We just have 2 types of statements. So 2 to the second power is 4 rows. Under the first letter, set half of those to true and half of those to false. True, true, false, false. And we're going to repeat that over here. You want to make sure you use the same values for the same letters. That's very important. Under the next letter, which is L, we're going to cut that number in half. If we had 2 trues and 2 falses underneath K, we're going to have 1 true and 1 false. 1 true and 1 false. And we're going to repeat that under every other instance of L. True, false, true, false. Back over here on the left, we have a disjunction, either K or L. So if at least one of the 2 statements is true, the disjunction will be true. That is the case in the first row. At least one of them is true. Same thing in the next row. Same thing in the next row. But in the last row, it's not the case that at least one of them is true. So we end up with false. And I'm going to circle that because those are the values underneath the main operator. For K and L, that's a conjunction, and a conjunction is true only if both conjuncts are true. So in the first row, we've got K and L both being true. That'll give us a true conjunction. But in all the other rows, it's not the case that K and L are both true, so we end up with falses all the way down. And I'm going to circle those values as the values underneath the main operator. Now you can see that these two statements, it's not the case that they have exact truth values. They're not equivalent. In other words, they don't contradict each other. They don't have exact opposite truth values. But what you can see here, and I'm going to highlight it in yellow for you, it's possible for both of these statements to be true. In the first row, when K and L are both true, those statements could both be true together. So these statements are consistent. Now, again, just to dwell on this just a minute, consistency doesn't mean that both statements are actually true, because maybe we live in this world where K is false and L is false. But if it's possible for the 2 statements to be true together, that shows that the 2 statements are at least consistent with each other. Although, again, just to be really clear, that doesn't mean that both statements are actually true. It just means that it's possible for them to be true together. Because each row of the truth table represents a different possible scenario, or a different possible case, or a different possible way the world could be. Let's look at a couple of statements that are inconsistent now by contrast. So these are from page 360 of your textbook. So let's let the first statement be K is equivalent to L, or K biconditional L. And let's let the next statement be K and not L. Okay. Same thing, we just have 2 simple statements, K and L. So we're going to need 4 rows. Under K, true, true, false, false. And under L, true, false, true, false. And we're going to repeat those values. Under K, true, true, false, false. And under L, true, false, true, false. Let's start over here on the left. Remember, a biconditional is an equivalence. So if K and L have equivalent truth values here, that biconditional will be true. That's the case in the first row. In the second row, they don't have equivalent truth values, so you end up with a false biconditional. Same thing in the third row. But in the last row, they are equivalent. They're both false, so you end up with a true biconditional, or true equivalence. And I'm going to circle the values underneath that main column. Okay. Over here on the right, the main operator is this dot, but we can't figure that the values out for that dot yet, because that dot isn't connecting K and L. It's connecting K with the negation of L. So we need the values for that negation. And again, strictly mechanically speaking here, you start with the connectors with the smallest scope. And I think it's pretty clear here that this negation has a smaller scope than the dot. The negation just applies to L, whereas the dot applies to the entire statement. So we're going to start with the connective with the smallest scope, which is that negation. And if L is true, the negation will be false. And if L is false, the negation will be true. And vice versa all the way down. Rinse, repeat. Now, just to be really clear, this dot is connecting K and it's connecting not L. So the two columns that we care about for figuring out the values for that dot are the two columns that I've indicated there with the arrows. And it's conjunction. So the dot is true only if both of the two conjuncts are true. And here we have something true and something false. That'll give us a false conjunction. In the next row, we've got true and true. That'll give us a true conjunction. And in the next two rows, we'll end up with false. And I'm going to circle that column as the values underneath the main operator. Do just a little bit of cleanup here. Get rid of these arrows we don't need. Okay. So in looking at these two columns compared to each other, I think you can see there's no row in which the two statements are true at the same time. In the first row, the first statement is true, but the second statement is false. In the second row, the first statement is false and the second statement is true. Both statements are false in the third row, and in the final row, the first statement is true and the last statement is false. So there's no row in which these two statements are true at the same time. That means these two statements are inconsistent with each other. Now notice they're not contradictory either. They don't have exact opposite truth values. In fact, there's one row here, right here and right here in the third row, where the two statements have the same truth value. So they don't have exact opposite truth values. So inconsistency does not mean the same thing as two statements being contradictory. Inconsistency means there's not one row where the statements are true at the same time. So those are some things you can learn about pairs of statements using truth tables. Let's do a couple of examples from the exercises from section 6.3 of your textbook, and then we'll move on to talk about determining the validity or invalidity of arguments with truth tables after that. Okay, let me pick a couple of exercises from our textbook to do. Let's do one with 8 rows in it. Let's see here. So I'm going to pick number 9 from your textbook. So this is 6.3, Roman numeral number 1, number 9. Okay. So we've got a fairly lengthy statement here. We've got X implies R implies F, all of that inside brackets. Then we've got a biconditional. Got another set of brackets. X implies R. All of that implies F, and then the end bracket. So I'm just going to highlight a couple things here. The main operator is this biconditional. I think that's pretty clear. That biconditional just connects that entire bracketed expression on the left with this entire bracketed expression on the right. So we're not going to be done until we get the values underneath that main operator. Let's dive in. One thing you should notice right off the bat is that there are 3 types of simple statements here, X, R, and F. So that's going to give us 8 rows. 2 to the 3rd power equals 2 times 2 times 2 equals 8 rows. Okay? Once you know the number of rows that you need, go underneath the first letter and set half of those to true and half of them to false. So true, 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 false, 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 false. Okay. Under the next unique letter, which is R, and if you had X there again, you'd skip that and go to the next unique letter, but here we just go over to the next letter, which is R. Cut that number in half. If you have 4 trues and 4 falses under X, here you're going to have 2 trues and 2 falses. 2 trues and 2 falses, all the way down. Go to the next unique letter, which is F, And we're going to cut that number in half. 1 true and 1 false. 1 true and 1 false. 1 true and 1 false, starting at the top, going all the way down. And we're going to repeat those values everywhere those letters occur. So we have the letter X again over here. So we're going to copy that X column. True, 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 true. False, 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 false. Under R, 2 trues and 2 falses, repeating all the way down. True, true, false, false, true, true, false, false. And under F, true, false, true, false, true, false, true, false. Okay. So again, we're going to start with the connectors that have the smallest scope and work our way outward until we get to the main operator. I'm going to start over here on the left. With this horseshoe nested inside the parentheses, R implies F. And just to indicate where I am, I'm going to start with these two columns right here to get the values for that conditional between them. And a conditional is only false if you have a true antecedent and a false consequent. So in the first row, you don't have that, so the conditional will be true. The next row, we do have a true antecedent and a false consequent, so that conditional will be false. Here we end up with true and true and true, but here's another row where we have a true antecedent and a false consequent, so that'll be false and true in the last two rows. And I'm going to erase my little placeholder marks. Okay. Now to figure out the value of this horseshoe operator right here inside the brackets on the left, we need the values for X, and we also need the values for this conditional inside those parentheses. Those are the two things that are being connected by that conditional operator, by that horseshoe. So we've got something true implying something true. That'll give us a true conditional. Something true implying something false. That'll give us a false conditional. Something true implying something true. That'll give us a true conditional. True implying true. That's a true conditional. False implying true. That's a true conditional. False implying false, that's a true conditional. And again, if I've lost you at this point, go back to week 2 and make sure you understand the definitions of these logical operators. Something false implying something true, that'll give you true, and something false implying something true, that'll give you true. Okay, we're not done. That's just the left side of the expression. Let's go over here and do the same basic thing on the right. Starting on the inside and working our way out now, X implies R. We have true implying true, that'll give us true. True implying true, that'll give us true. True implying false will give us false. True implying false again will give us false. And if you notice, we're going to end up with true all the way down because the antecedent is false on the left. Okay. Now we need the value for this horseshoe operator. And that horseshoe operator is going to connect these two columns. It's going to connect that horseshoe inside the parentheses, and it's going to connect the values for F. So we end up with true implying something true. That'll give us true. True implying false will give us false. False implying true will give us true. False implying false will give us true. True implying true will give us true. But in this next row, true implying false will give us false. True implying true will give us true. And true implying false will give us false. Okay, we're almost done. Now we need the value for this biconditional in the middle, and I'm going to do that in a different color just for clarity's sake. Here we go. So really quickly, this biconditional connects this entire expression on the right in the bracket with this entire expression on the left in the brackets. But the main operators inside each of those brackets are right here. The horseshoes that I've indicated with the two yellow arrows underneath. So those are the two columns that we're going to use to determine the values for this biconditional. So let's go through these. We've got something true is equivalent to something true. They are equivalent, so that gives us true in the first row. We have false and false. They are equivalent, so we end up with true. Here, I'll circle them as I go. In the third row, we've got true and true. They're equivalent, so we end up with true. We have true and true. They're equivalent, so we end up with true. We have true and true. They are equivalent, so they end up with true. We end up with true. In the next row, however, notice that we have something true and something false. They are not equivalent, so we end up with a false right there. In the next row, we have true and true. That'll give us a true statement, and true and false. That'll give us a false statement. So now we can ask the question that we started out by asking, what type of statement is this? Is this a logical truth or a self-contradiction, or is it a contingent statement? I'm going to circle the values underneath that main operator. And you can see here that this is not a logical truth. It's not a tautology, because it's not the case that all the rows are true. They're not all false either. They're sometimes true and sometimes false. You know, some rows like this are true and some rows like that are false. So this is a contingent statement. Means it's sometimes true and sometimes false, depending on which way the world is. In other words, depending on which row of this truth table represents the actual world. If we'd ended up with all truths, we'd have a tautology. If we'd ended up with all falses, we'd have a self-contradiction. Okay, let's do an example from the next section of exercises, comparing two different statements to each other. So I'm going to pick an interesting example. Let's do number 7. So just to make it easy to find for you, this is section 6.3, Roman numeral number 2, and exercise number 7. Okay, so we are given two statements. First statement is, if E implies C, then L. And the second statement is, E implies that C implies L. Okay. So notice here we have 3 types of simple statements, E and C and L. So that's 2 to the 3rd power equals 8 rows. Okay. Under the first letter, set half of those rows to true and half of those rows to false. Under the next unique letter, which is just the next letter over, 2 trues and 2 falses. 2 trues and 2 falses. And under the next unique letter, 1 true and 1 false, 1 true and 1 false, all the way down. That'll exhaust all the possible combinations of truth values. And we're going to repeat those values in the next statement. So take that E column and repeat it here, 4 trues and 4 falses. Oops. Always good to catch your mistakes as you go. 4 trues and 4 falses. Probably a good idea to do this in pencil on your homework, by the way. You think you can see that if you do this in pen, it's very easy to make a mistake and you end up having to start over. So I would do your homework on pencil if I were you, but it's up to you. And we're going to repeat the L column, 1 true and 1 false, 1 true and 1 false. Little tedious. That's okay. Got more time than money. So we're going to start in each statement. We're going to start with the operator in the innermost parentheses with the smallest scope and work our way out until we get to the main operator. So in this first statement, we've got a conditional inside parentheses. E implies C. Remember, a conditional is only false when you have a true antecedent and a false consequent. So let's run down the list here. True implies true. That's true. True implies true. That's true. True implies false is false. True implies false is false. False implies true is true. False implies true is true. False implies false is true. And false implies false is true. Then we can get the value for this conditional that's the main operator of this first statement. So the two values we're going to use are this value underneath this first conditional inside the parentheses and the value for L. So we have something true implying something true. That's true. Something true implying something false, that's false. Something false implying something true, that's true. Something false implying something false, that's true. True implying true, that's true. But here we have something true implying something false, and that would be false. Then we have something true implying something true, that's true. And in the last row, something true implying something false, that is false. And I'm going to change colors and I'm going to circle that column underneath that main operator. Those are the values we care about. All the other values are just extraneous information at that point. We're going to do the same thing on the right. In fact, let me get rid of this note here. There we go. A little cleaner on the eyes. Start with the connective with the smallest scope inside the parentheses and work our way out. So inside the parentheses, we have C implies L. So true implies true is true. True implies false is false. False implies true is true. False implies false is true. True implies true is true. But here's our weird case where we have true implying false. That's false. False implies true is true. And false implies true. False implies false, excuse me, is true. Now, the two values that we care about for this main operator are the values for E and the values we just figured out, because that horseshoe inside parentheses is the main operator of what's inside the parentheses. But the main operator of the overall statement is this horseshoe right here, and the two values we care about are this value and this value. So we have something true implying something true. That would be true. Something true implying something false. That would be false. Something true implying something true. That's true. Something true implying something true. That's true. And if you notice, we have falses as the antecedent all the way down from there. So these are all going to be true. And we can just skip ahead a little bit and fill those out. Now I'm going to circle that column because those are the values we care about, like so. So now we can compare these statements and ask a few questions. Are these statements identical in every possible row? And let's take a look. In the first row, they're both true. In the next row, they're both false. The third row, they're both true. The fourth row, they're both true. In the fifth row, they're both true. But in the sixth row, one is true and the other one is false. So these are not contradictory. They don't have exact opposite values. They don't have exactly the same values. And there's no term for that. If it's neither equivalent nor contradictory, there just is no term for that situation. So the next thing we can do, we can ask whether these statements are consistent or inconsistent. So what you're looking for there, you're looking for a situation where at least one of the two rows, the two statements are true together. And if you even, that happens right in the very first row right here. There's at least one row where the statements are both true, and that shows these statements are consistent. Because there's at least one row where the statements are true at the same time. So that's how you go about comparing two different statements using truth tables. And you get a lot of practice on this in your homework. So again, make sure you do, I'm preaching to the choir here, but make sure you watch the videos, of course. Make sure you get some practice on the exercises that are given as examples in the textbook reading, even before you get to your textbook exercises. I think you can see that truth tables are going to take a long time to do. What I'm not looking for, I don't just want the answer, I want to see your actual truth table. So make sure you're doing this on paper and submitting screenshots of your actual work, either on paper or as screenshots. But if I can't see your actual truth tables, I can't see that you're getting the answers in the right way. So please show all your work when doing your exercises. Okay, now I want to move on to section 6.4 of your textbook to talk about truth tables for arguments. So if you remember, in deductive logic, the main term is validity. And the validity of a deductive argument has to do with whether or not the conclusion follows from a set of premises. And in a valid argument, if you have a number of premises, like premise 1, premise 2, premise 3, and some conclusion is supposed to follow from those premises, if the premises are all true, that means it's impossible for the conclusion to be false, right? That can't be the case. In a valid argument, the conclusion is supposed to follow from the premises. So if the premises were true, if you assume that the premises are true, that conclusion has to be true if the argument's valid. Now, fortunately, you can evaluate the validity of arguments on a truth table, and I think you can see why. If each row represents a different possible combination of truth values, you should be able to check row after row after row in the truth table for an argument. And if you find a row where the premises are all true, but the conclusion is false, that shows that the argument is invalid. It shows that the conclusion doesn't follow from the premises. But if you don't find a row like that, that will show that it's impossible for the premises to be true and the conclusion to be false, and that would make the argument valid. So let's do a couple simple examples of this. I'm going to do a couple of examples from your textbook. These are from page 365 in your textbook. So let's look at a very simple example. Here's a simple argument. J implies E, that's the first premise. Not J, that's the second premise. And the conclusion of the argument is not E. So if we want to evaluate this argument from validity, what we do is we do a truth table for every statement in this argument side by side. So I'm going to rewrite these statements side by side. J implies E. I'm going to use a single slash to separate the premises from each other, not J, and a double slash to separate the conclusion. Okay, it's the same statements. J implies E, not J, and the conclusion is not E. And now I want to complete a truth table for these statements. There are only two simple statements, J and E, so we're only going to need 4 rows. Underneath the first letter, we're going to set 2 of those rows to true and 2 of those rows to false. Under the next unique letter, which is E, 1 true and 1 false. 1 true and 1 false. And if it's not clear why I'm doing that, you need to back up this video and watch the first part of the video again. And then we're going to repeat those values everywhere these letters occur. So under J, true, true, false, false. Under E, true, false, true, false. Okay, now we need to complete the truth tables for each of these statements. Starting over here on the left, J implies E. That's only going to be false if J is true and E is false. That happens right here. In all the other rows, you're going to end up with a true statement. And I'll circle that to indicate that that's the value that I'm interested in for that statement. Okay. For not J, if J is true, true, false, false, we're just going to have false, false, true, true. And the main operator there is, of course, the negation. So I'm going to circle the values underneath the negation. Those are the values for that statement. And same thing for E. If E is true, false, true, false, the negation would be false, true, false, true. And I'm going to circle those values. Okay, and now what I'm looking for one row, a horizontal row, where the 2 premises are both true, but the conclusion is false. And I found one right here in the 3rd row. The 2 premises are both true, but the conclusion is false. And that shows that the argument is invalid. And the reason is this. If you remember, if the argument were valid, if the premises are both true, that should guarantee the truth of the conclusion. But that's not what's going on here. We have a case where the premises are both true, but the conclusion is false. That shows that the conclusion does not follow from those premises and the argument is invalid. If we didn't find a row like that, the argument would be valid. So let's do one more, slightly more complicated example. Then I'll do an example from your textbook exercises and I will let you go after that. Okay, this is a slightly more complicated example from your textbook. We've got O implies not T. That's our first premise. Again, we're going to separate our premises with a single slash. The second premise is not T implies B. And we have a conclusion. So we're going to separate the conclusion off with a double slash. The conclusion is O implies B. So here we have 3 simple statements, O, T, and B. So we're going to need 8 rows. That's 2 to the 3rd power, which is 2 times 2 times 2, which is 8. So underneath that first letter, set half of those values to true and half of those values to false. 4 trues and 4 falses. Then go to the next unique letter, which is here underneath T, and we're going to cut that number in half. 2 trues and 2 falses. 2 trues and 2 falses. All the way down. Oh, I made a mistake. Right there. Catch myself doing that sometimes. If you make a mistake, catch yourself. Use pencil. True, true, false, false, true, true, false, false. Then we're going to go to the next unique letter. Now notice here if we move the next letter over, we have T again. So we're going to skip that and go to the next unique letter, which is B. And we're going to cut that number in half. If we had 2 trues and 2 falses underneath T, 1 true and 1 false. 1 true and 1 false, 1 true and 1 false, all the way down. And we're going to repeat those columns everywhere else they occur. So here we have another instance of the letter T. So we're going to repeat the T column, 2 trues and 2 falses, 2 trues and 2 falses. Okay. Under the next instance of O, we're going to repeat the O column, true, 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 false, 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 false. Underneath B, we're going to have 1 true and 1 false. 1 true and 1 false. same as the previous B column. Okay, let's complete truth tables for each of these statements. For the first statement right here, we can't figure out the value for that horseshoe until we figure out the value for that negation. So let's figure out the value of the negation. It's just the opposite values of t. So if t is true, the negation is false. And if t is true, the negation is false. If t is false, the negation is true. And so on and so forth. Just the opposite values of t. Okay. Now, to figure out the values for this horseshoe, we need to compare the values of O with the values underneath that tilde. Those are the two things that are being connected by that horseshoe. And there's only one case when the horseshoe is false. That's when the antecedent is true and the consequent is false. And that's what we have right in this first row. Same thing in the next row. But in the third row, we have true implies true. That's true. Fourth row, true implies true. That's true. And if you notice, because we have falses all the way down on the left, we're not going to end up with true and false. So we're going to end up with a true conditional all the way down. I'm going to circle those values because those are the values for that statement that we care about. Okay, let's complete the truth table for the second premise. Not T implies B. Again, the main operator here is the horseshoe, but we can't figure that value out yet because the horseshoe is connecting not T with B, and we don't know the values for the negation of T yet. We just know the values for T. So we're going to start with the connective with the smallest scope, which is that tilde, and that has the opposite values of T. So if T is true, that negation will be false. And if T is false, the negation will be true. So on and so forth, all the way down. Then we're going to compare the values of this tilde with a value for B using the rule for the horseshoe. So if the antecedent is true and the consequent is false, we'll end up with a false statement. Otherwise, we end up with a true statement. So here we have false implying true. That'll give us true. False implying false. That'll give us true. True implying true. That'll give us true. But here's a case where we have a true antecedent and a false consequent. That will give us false. False implying true. That's true. False implying false. That's true. True implying true, that's true. And here's our weird case again, true implying false, that's false. And I'm going to circle the values underneath that operator because those are the values we care about for premise 2. Okay, in the conclusion, we just have O implying B. So we're just going to follow the rule for the horseshoe. True implying true, that's true. True implying false, that's false. True implying true is true. True implying false, that's false. False implying true is true. False implying false is true. False implying true is true. And false implying false is true. And I'm going to circle the values for that column. So once I've completed the truth table for each statement, the two premises and the conclusion, what I'm looking for is a case where the two premises are both true, but the conclusion is false. If I find one, the argument is invalid because that shows that the conclusion does not follow from the premises. If I don't find one, that means the argument is valid. Very easy to confuse those, mix them up, and get them backwards. If you find a row where the premises are both true and the conclusion is false, that means it's a bad argument, an invalid argument. It means the conclusion does not follow from the premises. If you don't find a row like that, the argument is valid. Okay, so let's see what we can find here. Is there a row where the premises are both true? I see that right here. Premises are both true, but the conclusion's true over there on the right. So that row is okay. We've got another row where the premises are both true, but the conclusion's true. Same thing in the next row, true premises, but the conclusion's true. True premises here, but the conclusion's true. So there is no row where the premises are all true, but the conclusion is false. That means this argument is valid. We did not find a row where the premises are all true, but the conclusion is false. So this is a valid argument. Okay, let's do an example from your exercises. And actually, we'll probably do two examples. We'll do a simple example and a more complex example. And that will be all I have for you for today before you dive into your exercises. Okay, so I'm going to do number 4 from Hurley section 7.4, Roman numeral number 2, number 4. So we're given an argument. We are given the negation of G and M as one premise. We're given M or not G as the second premise, and the conclusion, which I'm going to separate out by a line there, is not G. So what I'm going to do, I'm going to write all three of these statements side by side. We have the negation of G and M. I'm going to separate each premise with a slash, M or not G, and I'm going to separate off the conclusion with a double slash, not G. Okay. Notice we only have two types of simple statements here. We have G and M. So we're only going to need 4 rows. Under the first letter, 2 trues and 2 falses. Under the next unique letter, which is just M, 1 true and 1 false. 1 true and 1 false. And we're going to repeat those columns everywhere they occur. So under M, we're going to copy the M column. True, false, true, false. Under G, we're going to copy the G column. True, true, false, false. And here, under G, we're going to copy the G column once more. True, true, false, false. Okay. Now we need to start with the connectors with the smallest scopes and work our way outward until we get the values for the main operator in each of these 3 statements. I'm going to start way over here on the left. The main operator in the first premise is this dot, but we can't do that yet because we don't have the value for this negation. The dot is connecting negation of G with M. We just know G. We don't have the negation of G yet. So start with the connector with the smallest scope, which is that tilde in front of the G. If G is true, that tilde will be false. And if G is false, that tilde will be true. Okay, now we can figure out the value for the dot. Again, the 2 columns we care about for figuring out the values for the dot are those 2 that I've indicated with a small arrow. We have something false and something true. They're not both true, so we end up with a false statement. False and false, that's going to be false because they're not both true. But in the third row, the 2 values are true, so we end up with a true conjunction. And in the last row, they're not both true, so we end up with a false conjunction. And I'm going to circle the column underneath that main operator to indicate that those are the values for that statement that we care about. Okay. In the next premise, the connective with the smallest scope is this tilde in front of the G. So let's figure out the values for that. If G is true, the tilde will be false. And if G is false, the tilde will be true. Now, the 2 columns we care about to figure out the value for that wedge are this column, M, and the column underneath the tilde, because that's what's being connected by the wedge. The wedge is connecting M, and it's connecting not G. So we have something true and something true or something false. That will be true because at least one of the 2 is true. The next row, we have false or false. That's false. The next row, we have true or true. At least one of them is true, so we end up with a true statement. And in the last row, we have false or true. At least one of them is true, so we end up with a true statement. And I'm going to circle those values. And the last statement, the conclusion of the argument, is pretty straightforward. It's just the negation of G. If G is true, that negation will be false. And if G is false, that negation will be true. And I'm going to circle that column. You can see this, these short examples don't take very long to do. What I'm looking for now, I'm looking for a row where both premises are true and the conclusion is false. In the first row, both the premises aren't true. We've got false and true. In the next row, both premises aren't true. In the third row, both premises are true, but the conclusion is true. And in the last row, both premises aren't true. So there is no row where the premises are both true and the conclusion is false. That means this argument is valid, because there's no row where the premises are true and the conclusion is false. In other words, it's impossible for the premises to be true and the conclusion to be false. That means the conclusion follows from the premises by necessity. Okay, let's do a slightly more complicated example, and I'll give you your time back. Okay, I'm going to do a fairly lengthy example. I'm going to do number 20 from this section. And I'm actually, I need some different paper here. Give me a second to switch papers. Give myself a few more lines. Here we go. Okay. So this is going to be section 7.4, Roman numeral number 2, number 20. And we are given 4 premises and a conclusion. So this is going to be fairly large, but that's okay. The first premise is not A or R. We're going to separate the next premise off with a single slash. The next premise is the negation of in and not C. Next premise, we've got R implies C. Next premise, we've got C implies not N. And the conclusion, which I'm going to separate off with a double slash, is just A or C. So the first thing we need to do here is figure out how many rows we're going to need. So let's count the number of simple statements we've got. We've got A, R, N, and C. So we have 4 statements. That's 2 to the 4th power. That equals 16 rows. So this is going to be a fairly lengthy truth table. Just to keep things a little visually clearer, I'm going to switch colors here and do my truth values in yellow. So if we know we're going to need 16 rows, we need 8 rows of true and 8 rows of false. So starting here, we've got true, 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 true. That's 8 rows of true. And we're going to need 8 rows of false. False, 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 false. 8 rows of true, 8 rows of false. Then we're going to go to the next unique letter, which is R, and we're going to cut that number in half. 4 true, 4 false. Oops. Always catch your mistakes as you go. True, 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 false, 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 false. True, 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 true. False, 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 false. Okay. Then go to the next unique letter, which is N. We're going to cut that number in half. True, true, false, false. 2 trues and 2 falses. Then we're going to go to the next unique letter, which is C. And we're going to cut that number in half. 1 true and 1 false. Alternate all the way down. Believe me, you will be very thankful to move on past truth tables after this homework assignment. This is probably the most tedious thing you'll have to do the entire semester is fill out a truth table this big. And we're going to copy those columns all the way across. So under the R column, we're going to have 4 trues and 4 falses. 1, 2, 3, 4, and then 4 falses. 1, 2, 3, 4. True, 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 true. False, 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 false. Under C, remember we're going to copy the same column from before. So we already filled out C, which is 1 true and 1 false, alternating all the way down. We're going to do the same thing here. True, false, true, false, true, false, true, false, true, false, true, false. I think it's helpful to say it out loud. Helps you keep your place. All the way down. We have a C column again, so true, false, 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 true, false. Under N, we're going to copy the N column, so that's 2 trues and 2 falses, alternating all the way down. So true, true, false, false, true, true, false, false, true, true, false, false, true, true, false, false. Under A, that was our column with 8 trues and 8 falses. So 1, 2, 3, 4, 5, 6, 7, 8, and 8 falses. 1, 2, 3, 4, 5, 6, 7, 8. I feel like we should be doing a dance or something. Under C, we have 1 true and 1 false. That's our C column. True, false, 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 true, false. Okay, those are our initial truth values. Now we need to start computing the values of each statement, starting with the connectives with the smallest scope and working our way outwards until we get to the values underneath the main operator for each statement. I'm going to start on the very left. The main operator is this wedge, but we can't figure that out until we have the value of the negation of A. So if A is true, not A will be false, and vice versa. So we have 8 falses here. False, 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 false. And then we switch to true, 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 the opposite of A. Now, to figure out the value for this disjunction, the two values we care about are the values underneath this negation and the values underneath R. And we're going to use the rule for a disjunction. And a disjunction is an either or statement. So if either of those two values is true, we end up with a true disjunction. So here we have something false implying something, or excuse me, something false or something true. That will be true because at least one of the two is true. Same thing here, same thing here, same thing here. Notice though, in the next 4 rows, we have false or false, that'll be false. False or false, that will be false. False or false will be false, and false or false will be false. In the next 4 rows, we have true or true, that's true. True or true, that's true. True or true, that's true. And true or true, that's true. And in the last 4 rows, we have true or false, which is true because at least one of the two is true. Same thing here, same thing here, and same thing here. And I'm going to use a different color here. I'm going to circle these in green to make it clear which values we care about. So again, I'm just circling the values underneath that main operator now. So everything else is a distraction at this point. Okay. Let's move on to the next statement. So we start with the connectives with the smallest scope, which would be that C, that negation in front of the C. So this negation will have the opposite values of C. False, true, false, true, false, true, false, true, all the way down. Okay. Next, we need to figure out the value for that dot, and the dot connects in and it connects the negation of C. So we're going to use this column and that column. So we have true and false, that is false. True and true, that's true. False and false is false. False and true is false. Remember, we're looking for cases where both conjuncts are true. That'll give us a true conjunction. If we don't have that, we'll end up with a false conjunction. So false. Here's a case where they're both true, not both true, not both true, not both true. Here they're both true, so that's true. Not both true, not both true, not both true. Here they're both true, not both true, and not both true. But we're not done yet. Notice that this negation here in the second premise in front of in and not C, that negation is the negation of that conjunction. And I want to make this really explicit just to make sure you're getting it. So this negation here negates this entire set of parentheses, but the main operator inside those parentheses is, is that dot. So that negation has the opposite value of the dot because that dot is the main operator of the thing that's being negated. So for each value of this dot, we're going to write the opposite of that underneath this tilde. So if the dot is false, the negation will be true. If the dot is true, the negation will be false. If the dot is false, the negation will be true. If the dot is false, the negation will be true. If the dot is false, the negation will be true. Same. If the dot is true, the negation will be false. If the dot is false, the negation will be true. If the dot is false, the negation will be true. The dot is false, so the negation is true. Next row, the dot is true, so the negation is false. In the next row, the dot is false, the negation is true. In the next row, the dot is false, the negation is true. Dot is false, so the negation is true. Dot is true, so the negation is false. Dot is false, so the negation is true. And the dot is false, so the negation is true. And I'm going to circle the values underneath that tilde because that tilde is the main operator of the second premise. like so. Okay. In the third premise, this is pretty straightforward. It's just a conditional. And remember, a conditional is only false if the antecedent is true and the consequent is false. We don't have that here, so in the first row, so the conditional is true. That is the case in the second row. We have a true antecedent and a false consequent, so the conditional is false. True. Here's that case again with a true antecedent and a false consequent. True here, true here, true here, true here. True here, but here's that case again with a true antecedent and a false consequent, so that will be false. Here's true. Here's that case again, true antecedent and a false consequent, and if you notice, it'll be true all the way down. And I'm going to circle those values, because that is the main operator of the, main operator of the third premise. There we go. Okay. For the fourth premise, we need to figure out the value of that negation symbol before we can figure out the value of the horseshoe. And that's just going to have the values opposite of the values for n. So if n is true, that negation will be false. And if n is false, that negation will be true. And vice versa. So false, false, true, true, false, false, true, true, false, false, true, true. Now to figure out the value for that horseshoe, we need to compare the values under C with the values underneath that negation using the rule for the horseshoe, which is, again, if you have a true antecedent and a false consequent, that's what we have here in the first row, we end up with a false conditional. Otherwise, you end up with a true conditional. So here's that one case where we end up with a false statement. True, true, true. Here's that case where we end up with a false statement. True, true, true. Here's that case again. And true, true, true. And I'm going to circle that column. Like so. Okay. Finally, we can do the conclusion. That's just a disjunction. If either of the two statements is true, we end up with a true disjunction. So that's the case here. That's the case here. Lots of trues. Same thing here, but here's a case where we don't have at least one of them being true, so we end up with a false disjunction. True, false, because it's not the case that at least one is true. And we end up with true here, true here, and false here. And I'm going to circle those values. Okay, we're almost done. So the first step is just to make sure you've completed the truth table correctly. Assuming you've done that, what you're looking for now is a row, any row, at least one row, where all the premises are true and the conclusion is false. And if so, what I'm going to do, I'm going to use a different color here. If I find one, I'm going to mark that row with a little asterisk or a star off to the right. And if I don't find one, I'll know the argument is valid. So in the first row, the premises aren't all true. We have true, 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 false. So I don't care about that row yet. Next row, true, false, false, true. The premises aren't all true. On the third row, the premises, in fact, I'll indicate it here with a little arrow. In the third row, the premises are all true, but the conclusion's true, so that's okay. In the fourth row, the premises are not all true, so I don't care about that row. In the next row, we have not all true premises. I don't care about that row. Next row, premises aren't all true, so I don't care about that row. Same thing in the next row, premises aren't all true. Same thing here. Let's see, here, premises aren't all true. The next row, premises aren't all true. In the next row, the premises are all true, but the conclusion is true, so that row is okay. In the next row, the premises aren't all true. In the next row, the premises aren't all true. And in the next row, the premises aren't all true. Next row, the premises are all true, but the conclusion is true. But in the very, very last row, they really make you wait for the punchline here. In the very, very last row, the premises are all true, 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 but the conclusion is false. So I did find at least one row where the premises are all true, but the conclusion is false. That shows that this argument is invalid because it's possible for the premises to be true and the conclusion to be false. And I really want you to understand this, that in a And a valid argument, if the premises are all true, that should guarantee that the conclusion would be true. So the fact that we found a row where the premises are all true, but the conclusion is false, that shows that this conclusion does not follow from that set of premises and the argument is invalid. Okay, that's all I have for you guys for today. Make sure you turn in your homework for week 3 by the end of Sunday at 11:59 p.m. Definitely let me know if you have any questions. Make sure you're showing all your work. I don't just want to see your answers. I want to see the actual truth tables, which means you might have to do this on paper, take a screenshot, or use your cell phone and take a picture of each exercise, put it all into a PDF and send that to me. I want to see your actual work. You could also do it in tables inside a Word document. That would be fine. But if I can't see your actual truth tables, I have no confidence that you're doing these exercises in the right way. In other words, the method is just as important as the actual answer. So that's all I have for you guys. Hope you guys have a great week. Let me know if you have any questions, and I'll look forward to seeing you again in the video for week 4. Have a great week.